This video is a quick summary of what we did in section 8.3 and answers a couple of example problems so that you will have a good chance of doing the 8.3 homework before Monday. Where we left off on Thursday this week was coming up with this formula for the sum of a geometric series. And the short version of it is that if we have a geometric series, meaning that we have a first term, and then we have that term times a ratio, plus that term times a ratio squared, plus that term times a ratio cubed. So we would say this is a geometric series with common ratio r. All we need to know is the first term, a, and the common ratio r, and the formula for this sum will be a over 1 over 1 minus r. And this happens, this works anytime the common ratio is between -1 and 1, and if the case where the ratio is not between -1 and 1, then the series diverges. So for geometric series, we really know everything. As soon as we can identify the first term in the common ratio, we know immediately if it diverges or converges, and in the cases where it converges, we have a formula that tells us exactly what it converges to. So in class, we had several problems that allowed us to practice using the formula. The first one is a little ugly looking because it's got a weird number in the parentheses, but the key is just realize that is just a number. If you step aside of the calculator and figure out what e to the minus 3 halves is, it's around, I think it was around 0.22. So that is a number. It is between -1 and 1, and so the series given in number 1 converges, and the formula for what it converges to is in terms of the first term in the common ratio. So if I write out the first few terms, which is always never a bad idea, we'll have that. Let me erase this. We'll have that number to the 0 power, that number to the first power, that number to the second power, and so on. And so that's enough to identify that my first term is 1. That's e to the minus 3 halves to the 0 power is 1. And the common ratio, the number that this is based on is e to the minus 3 halves. So these are powers of e to the minus 3 halves, or another way of saying it is that the ratio between successive terms is e to the minus 3 halves. So therefore this converges to 1 times 1 over 1 minus the common ratio. So again, first term times 1 over 1 minus r. The second one, it's easier to tell what the ratio is. The ratio is -5/7 there, and that again is between -1 and 1. But the first term here is not 0. If we were to write out a couple of terms to get some sense of what's happening. Here, the first term is -5/7 squared, and the common ratio is -5/7. So again, a times 1 over 1 minus r. And in the last one, it's not quite as obvious until you realize that, and I think I said this in class, but 2 to the -4 times j is the same thing as 2 to the -4 all to the j power. So this is 2 to the -4 to the first, plus 2 to the -4 to the second, plus 2 to the -4 to the third, and so on. And so 2 to the -4 is 1 over 16. Again, that's a ratio r that's between -1 and 1. So this converges, and the limit is the first term times 1 times 1 over 1 minus r. So that's the bulk of the problems that are in section 8.3. There are a couple of problems where they ask you to find finite sum, and so I wanted to show you one example of that, because if you don't have a calculator in front of you, this may seem like a kind of a time-wasting task, because it may ask you to add up 15, 20, 30 terms of a series without, if you don't have a calculator, that may seem like a daunting task. But what I want to point out is that you can actually figure this out using that easy sum of the infinite geometric series formula if you want to. The key is to just let the series go on forever. So if I first write down the series k equals 1 to infinity, and I'm going to rewrite the thing that I'm summing there so it's a little more obvious what the formula is. The thing that I'm summing there is the same as that. So instead of 2 over 3 to the k, we could think of that as 2 times 1/3 to the k power. Just take a second to make sure you believe the algebra that those are the same. And so that's what we get across the first line here, is just this infinite series. The nice thing is that we know that that has a first term of 2/3 and a common ratio of 1/3. And if you resolve those fractions, you actually get 1. So the series that I have in the top line here, this whole thing, this infinite series, sums to 1. But I don't want that. I only want the first 20 terms. So what I'll do is I'll form the infinite series that starts with this 21st term and goes on forever. Again, the common ratio is 1/3, and so all I need to do to get the formula for that is take the first term, which is 2 over 3 to the 21, and multiply by 1 over 1 minus the common ratio, which, like I said, is 1/3. So the series across the top, this infinite series sums to 1. This infinite series that starts with 2 over 3 to the 21st sums to this guy. And so if you subtract the first line minus the second line, all you're going to have left is this stuff, which is what I want to know. So the difference between the first line and the second line is exactly the sum that I want. And so that's taking the answer 1 here minus this guy, and that's what I'm showing down here. And you can resolve this fraction just a little bit, and the final answer comes out to be 1 minus 1 over 3 to the 20th. And for this one, because you would be adding 20 terms, I think that's significantly easier. If all you had to do is add 6 terms here, then this seems like a really long-winded way to do it. So here's an actual problem from the homework. It involves adding 15 terms. So let's just do it real quick. From what I just said, this guy, and let me change colors back. This guy is 5/6 to the 0 plus 5/6 to the first, yada, 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 plus 5/6 to the 14th. So that's not an infinite sum, so I can't use my infinite series formula, but what I can do is form the series that does go on forever, which is exactly the same as this for as far as it goes. But this one just keeps going. Goes on forever. So to get the answer that I want, to get this answer, I see it right here. So what I would like to do is take the infinite series that I just wrote and subtract off this stuff from the end. So let me just pull this over here. The stuff that I just put the black brackets around, or the black box around, has this form. It's 5/6 to the 15th plus 5/6 to the 16th, and so on forever. That is a geometric series whose first term is 5/6 to the 15th and whose common ratio is 5/6. So the stuff that's in the black box here adds up to exactly this amount. This whole thing is a geometric series that starts with 1, 5/6 to the 0, and has a common ratio of 1/6. So this first line is 1 over 1 minus 5/6. So so this top line, this line, adds up to this. And if you deal with the fractions for a second, you'll see this comes out to be exactly 6. So this red box is 6 minus the stuff that I get here, subtracting this, which is equal to this. And again, this is 6. So I'll just write it that way. Maybe. So 5/6 to the 15th times 6. So this is my final answer to that problem. 6 minus 5/6 to the 15th times 6 will be the sum of just that part. Since this one's only adding 15 terms, you may decide that it's easier just to create those 15 terms and add them up. And certainly if you use a program like Excel or Mathematica that allows you to hold formulas instead of a calculator, that's a pretty easy thing to do. But this is another way to do it, particularly if you have to do a finite sum that has lots and lots of terms.